For those of you who are following on YouTube, I am terribly sorry that I didn't get to start the recording in time. So we are a little bit into the lecture. I will try to do my best to sort of quickly recap it, but I will suggest that you ask questions on mail or here in chat, and then we can discuss it further if there anything you are missing. But let me just it's not much that you have missed. So here we have the sun rotating around the sun, the Earth, which is the way that we would perceive it. But in reality, it's the Earth that is rotating or orbiting around the sun in the ecliptic plane, and we use the ecliptic plane to define the rotational axis of the planets. Here we have the different equinoxes and solstices. Like I said, we define the rectascension and declination from the spring equinox, which we have here, which is on the 22nd of March. Here we set it to 12 hours, 0 hours, and 0 degrees. At the summer solstice, as the 22nd of June, we set the rectascension to 6 hours and the declination to 23.5. At the autumn equinox, which is the 22nd of September, I'm pretty sure, we set the rectascension to 12 hours and again the declination to 0 degrees. And finally, at winter solstice, which is at the 22nd of December, we set the rectascension to 18 hours and the declination to 23.5 degrees. Like I said in the last lecture, we define the rectascension and the declination from the position of the sun at the spring equinox. And then we are back here, like I explained, when we have in the spring equinox, the time, the daylight time is the same all around the world. We still have daytime difference, but the day length will be the same because the rotational axis is parallel to the orbital direction. In the winter solstice, in the summer solstice, the North Pole will be in continuous daylight and the South Pole will be in continuous darkness. And as you move from the North Pole down to the South Pole, the nights will become longer and the days will become shorter. For the autumn equinox, we have the same situation here. The daytime length will be the same all the way around. And finally, we have here in the northern hemisphere, here we have the winter solstice, where the North Pole will be in continuous darkness and the South Pole will be in continuous daylight. It's a complete opposite to here. And then as you move further down south towards the South Pole, the daytime will become longer. And again, when I say daytime, I mean the time of the day where we have actual light. We could also say that the nighttime will be shorter, depending on how you want to define it. All right, now that we are going, so let's continue. As you can see here, the reason why we have winter solstice and summer solstice, let's take the example of winter solstice. And I'm sorry for those of you watching possibly from below the equator towards the south. It is simply defined for us here when we teach these things that when it's winter at the northern hemisphere, we call it winter solstice. And when it's summer at the northern hemisphere, we call it summer solstice. For those of you below equator, you are in your well rights to reverse the definition so that you have summer solstice at this point here and have winter solstice here. But just be aware that this is the way it's defined officially. So as you can see here, when we have the Arctic Circle, we can say that the sun does not rise above the Arctic Circle at winter solstice. Then we have the Tropic of Cancer, where the days are relatively short. The equator, that's the interesting thing. Around the equator, it's the exact same. Then we have the Tropic of Capricorn at the southern hemisphere. Here we have a longer daytime and shorter nights. As you can see, almost if you just look at the amount of line that you have here on the nighttime compared to the line that you have here on the daytime, it's not the exact correct way to do it, but it is a way to do it. You can definitely see that this line here is much longer than this line here. And on the opposite, if you look at the below equator at the Tropic of Capricorn, you can see that this line here is much shorter than this line here, indicating to some extent, relatively, that you have longer daytime and shorter nighttime. And finally, at the Antarctic Circle, you can see that it is completely in there's no shadow on that almost. So that means that the sun will not set here. And these, of course, are the sun rays. Don't have to explain that, hopefully. And when we take the summer solstice, it's the complete opposite. So I'm not going to go much into that. You can just see that for the Arctic Circle, there's no shadow on that, so the sun doesn't really set. If you take the Tropic of Cancer, you can see the complete opposite. You have a relatively short line of night here, shadow, if you will, and you have a long line of light, meaning that the daytime will be longer. And well, you can figure out the rest, right? But then look at the equator line here, because as you can see, this line here is exactly the same. So one of the things of living on equator is that you almost consequently have 12 hours of daytime and 12 hours of nighttime. But there are some smaller issues with the way that the Earth rotates and all that. It has a little bit of what's it called? That word will get to me. But it rotates a little bit special, so it changes a little bit. All right. If there are any questions to that, then put them in the chat right now. Otherwise, I will continue. So, what happens during an equinox? Well, like I said, this is the rotational axis of the Earth, and you can also say one thing was that I say it's completely parallel to the orbital direction of the of the of the Earth. Another way to say it is that you have the sun rays and the Earth tilt, this axis here, is completely perpendicular to the angle of the sunlight, meaning that no matter where you are on the Earth, you will get 12 hours. You can also see it here. If you draw a line here, if you draw a line here, if you draw a line here, no matter where you draw these lines like we saw before, you'll get 1/2 in light and 1/2 in nighttime. So no matter where you live on Earth during an equinox, you'll always get 12 hours of daytime and 12 hours of nighttime. Here we have the Zodiac. I'm not going to go much into that. And again, it's one of the Danish ones. I'll just try to sort of point it out. But the idea of the Zodiac is that we have these special constellations that are in special places during the different times of the year. So let me just try to quickly sort of point it out. So roughly you can say that in March, I can't remember what this is called. But we have the Virgin and the Lion. Yeah, wait a second. Let me just get the names for these constellations ready for you. There we are. Let me see. I need something that would give me a little bit more. Yeah, sorry about that. I didn't really. There we go. A little bit. I just need the names. So let me see. In this case here, we have it's Libra, the Virgin, Virgo, and Leo, the Lion. Those will be in Ecliptica, or in the Zodiac, if you will, during March. If we take roughly in December, you'll have, I think this is Pisces. No, that's the fish. So, a Cancer, of course, and the twins, or, sorry, just had Siri go wild on me. Let me see. The twins, what are they called? Gemini, of course. So we have Cancer, Gemini, and Taurus, or Taurus. Those are roughly in ecliptica during December, and then you could take during September. You have this is called Aquarius, and you have the Pisces, and you have Siri keeps going on. You have Capricorn. Those are roughly visible in September, and then finally you can say in June you'll have Scorpio, the Sagittarius. You'll have and you'll have let me see, Capricorn. Roughly, no, wait a minute. Steenberg. So that must be Aries. You'll have these in June, roughly. It's not very important because we're not going to deal much with with astrology here. But just so you know why we have defined these different zodiac signs, how they are defined. The problems with them, and obviously you can see they are sort of divided into each month. The problems, as you probably have heard a little while ago, is that the zodiac signs have changed their date. So, specifically, I was born in the sign of Taurus, and fortunately, you could say to some extent, I am still born in the sign of Taurus. But had I been born a little bit later or a little bit earlier, I would now have a new zodiac sign. So, in my opinion, that goes also sort of in the pool of evidence that the zodiac signs and astrology is more or less completely random. So I'm sorry to say, but that's just my opinion. But let's go on. So we're going to go a little bit more into sort of the nitty gritty number details of the Earth and the Sun relationship. For now, we have just taken more a qualitative look at it, but now we'll try to get a more quantitative look at how the interaction between the Sun and the Earth is, and why we experience summer, for instance, and winter. Because one of the interesting things is that actually during summer, the Sun is further away from the Sun than it is during winter. So why do we have these temperature changes? One of the names that you need to know for now is perihelion and aphelion. And what does that mean? It basically means for the Earth that at perihelion, the Earth is in its orbit the furthest, the shortest amount of distance away from the Sun. And contrary, or sort of the opposite, is in aphelion, where the Sun is the furthest away from the Sun. The Earth is furthest away from the Sun. And then we have a mean distance here, which we define exactly as 1 astronomical unit. This would be an AU and not an AE. This is because it's in Danish. I'm sorry about that. I went through these slides pretty quickly and corrected them, but obviously I didn't correct them enough. So we have in perihelium, it is 0.903 astronomical units. You have the raw numbers here. And in aphelium, it's 1.017 astronomical units. And if I'm not mistaken, aphelium is when we have summer, and perihelium is when we have winter. Roughly, I mean. Actually, I should say that aphelium is when we have summer solstice, and perihelium is when we have winter solstice. Roughly, yeah. Let's continue. So, I'm sorry about the quality of the images here. They are not very good, but it's the best I could do in order for you to be able to see what's going on, but I'll explain it. So when we have solar radiation, because of the tilt of the Earth, and this does not really have that much influence on the equator, but everywhere else this have a relatively big influence or higher influence. So in the summertime, you can say that the sun is high in the midday sky, meaning that if you sort of imagine a straight line down, you can't really do this, but just to sort of get an intuitive feeling of what this means, you can see that the amount of area that this little beam of light from the sun hits is a relatively small area. When I say relatively, it's because we have to compare it to something else, because I could easily tell you this is a small area and this is a big area. Now, compared to the house, it's a pretty big area, but compared to a man, it's a small area. So you can see it's relative to something. And you can see here what they say. So the shaft of sunlight is concentrated on a small area, which heats the ground effectively and make the days warm. This is contrary to the winter time, where the sun is low in the midday winter sky, like it says. So this is the midday summer sky. And you can see this beam of light is spread over a much larger area because of the angle. Now again, you can compare it to the house and you can say, well, it's still, but it is bigger. And that is why, and of course this is a qualitative drawing, so you should be able to see that this area here is larger. This area here is larger than this area here. So this is the reason why it's cold in the wintertime and warm in the summertime, even though the Earth is further away during summer. We can define two numbers to sort of give us an idea of how much light we receive from the sun. One solution is to define it as the solar output. That is given in the defined is the unit or the name A, and it's given by 4 times pi times radius to the second. The radius to the second is not the radius of the sun, but the distance to the planet that you want to check. So obviously the solar output for Mercury will be much higher than solar output for Pluto, for instance. We can also define another number that is much more relative to much more relevant for us here on Earth. First of all, I should say, which I didn't put in here, but if the flux, the solar flux, is equal to the luminosity of the sun divided by A, which is the solar output, and then we put that number in here. And the solar flux is given, the L is given as 3.9 times 10 to the 36 watts. So we can see now, if we take the distances, these different distances that we have, that during winter, which is here, we have a higher solar flux than we get during the summer, which is here. So it's 1434 watts per square meter here, and it's 1,342 watts per square meter here. And on average, it's the mean distance, it's 1,387 watts per square meter. So let's again take the example before we had with these different angles, but then again, let's make it more quantitative. Let's put some numbers in to try to calculate this. So in order to calculate how much solar radiation a given area receives, we can take sort of a square where the solar radiation hits that is 1 meter by 1 meter. That is 1 square meter. And then we can also add an angle. We tilt this box here, this solar beam here. And this angle will be h in degrees. And that means that our solar radiation suddenly becomes 1 divided by the sine to h meters. So finally we can say that our area is this here we got 1 over the sine to h times m in meters. So this is what we have here. This is the solar area that we receive when we have so the solar radiation we receive at a given angle where we put this in. And let me just give you an example quickly. Let me take my phone here and let's get a calculation here. So let's say we take 1 over sine to 0 degrees. It gives me Su. I'm not sure what the heck it means by that. Maybe it's because it's in radians. But if we get, it should give us that. Oh wait, no, now I know. It's because I've done it the wrong way. Let's take 1 over. I need to see how it's defined, right? So in this case here, we have the h in degrees is 90 degrees. So we need to take 1 over sine to 90 degrees. We get 1, which is what we expected. And again, if we take it to 0 degrees, we don't get any, and that makes perfect sense, right? Because if you imagine that the sunlight was completely parallel to the surface of the Earth here, then the sunlight wouldn't hit anything. But let's take, for instance, 1 divided by sine to 45 degrees. We'll get the square root of 2, which is 1.41. So as you can see, this will maybe it isn't radians. I'm not sure about this. It should give less than 1. Oh well, never mind. Let's no, the area. Yeah, no, sorry. Of course, the area gets bigger because that was what we expected. We expected when we tilted the light rays from the sun, it would get larger. So that's what we get. So in the case here, we have defined it. The reason why we used 1 square meter is that the meter becomes irrelevant for the calculation. So in the case where the sun is completely above us, we'll get 1 square meter. When we tilt the sun, at the angle of the sun that it hits the earth, we'll get a larger area lit. So now we can figure out, and again, I'm sorry a Danish word snuck in, but hopefully you can see it. At summer solstice, the culmination angle is 57.5 degrees for the sun, and the distance is closest to perihelion. The area is then A equals 1 over sine to 57.5 degrees, and that is for me here on Earth. 1.22 square meters, and the flux is then, at summer, 1,342 watts divided by 1.22 square meters give us 1,131.8 watts per square meter. Now let's take a look at what happens during winter solstice. At winter solstice, the culmination angle is 10.5 degrees, again for me here in Denmark, where I live, and the distance is closest to aphelion. The area then becomes A equals to 1 over sine to 10.5 degrees, giving us a whole area of 5.49 square meters. And the flux is then, at, again, the Danish word, winter, 1,434 watts divided by 5.49 square meters give us 261.3 watts per square meter. So even though the total flux that we get from the sun is a little bit higher during the winter solstice than it is during the summer solstice, we actually get much more radiation per square meter during the summer than we do during the winter. Let's take a look at the flux during equinoxes. You can hopefully imagine that that will be roughly I say, 34. That will be roughly the same, no matter whether it's at both equinoxes. So we have 34 degrees, and let me just go back, because now I would like to explain something that I didn't before. This H here is the culmination angle. So that was what I missed before that I told you about. So we have at the equinoxes, the culmination angle is 34 degrees. The culmination angle here for big H, meaning the sun, is the altitude, if you will, or the height above the horizon that the sun is above the Earth. So as you can see, at spring equinox, it's 34 degrees. Summer solstice is 57, almost 60 degrees. And again, at autumn, it's 34 degrees. And at winter solstice, 10.5. So it's relatively low. Let's go forward again. So again, we take at the summer, at both equinoxes, the culmination angle is 34 degrees. And we can assume the distance to be mean, of course. The area is then A equals 1 over sine to 34. I'm missing a parenthesis here. 34 degrees. It's 1.79 square meters. And the flux becomes S equinox 1,387 watts divided by 1.78 square meters is 775 watts per square meters. So as you can see, and this is very interesting in my opinion, not only does it explain why it's warmer during the summer and it's cold during the winter and why it should be relatively the same roughly. There are some weather changes, right? Because the way things work, the way the atmosphere works and all that. But generally speaking, during the equinoxes, we have roughly the same solar radiation, whether we are at the winter equinox or the at the autumn equinox or the spring equinox. Roughly the same. Like I said, if there are any questions for this, you put them in the chat and I'll try to answer them as quickly as I can or to my best ability. Other than that, you can also write mails to me to clarify if you have questions. I'll try to answer them as quickly as I can. In the next lecture, we are going to take a closer look at the sun, our new star. And then the next lecture again, we're going to talk more about the Earth and the Moon. And then we will move on to a relatively new chapter in these lectures. I hope that you have learned something. I do also hope that you have enjoyed yourself during these lectures here. I do not intend for this to be sort of entertaining or fun to watch, but I do hope that it's useful and it's educational for you. And I also hope that I will see you in the next lecture. If you like my lectures and if you want to see more from me, I am contemplating on doing sort of a weekly podcast about certain articles, a given subject that I found interesting, and then we can sort of discuss the content of these articles that I found and read. And I'll also try to give you sort of a broader perspective on news in astronomy and all that. I'll try to keep myself updated and then try to keep you updated. If you have interest in that, then please subscribe to my channel and then we can or follow it, if you will. and then then you can be notified whenever I give up a new lecture or do something else. I will try to put it in the plan to my best ability, but sometimes something just comes up that I need to go online with right away. All right. I'll hope that I'll see you in the next lecture. And remember, if you came late to this lecture, you can always watch it on YouTube when I've put the lectures out. All right. Hope to see you in your next one. Bye bye.